Hello, am I audible? If someone can let me know in the chat or by unmuting, am I audible? Can you hear me? Hello? Okay, so let's wait 2 more minutes. Let's see if anyone else joins. Okay, so let's begin then. So welcome again to the problem solving session for week 5 of the course Advanced Power Electronics and Control, which is taught by Professor Avik Bhattacharya. My name is Saleh Khan and I am a PhD student at IIT Delhi, and I'll be conducting these problem solving sessions. So in week 5 of the course, the topics that were taught were non-isolated converters were continued, and then different types of choppers were introduced, and finally isolated converters were taught. So, so the non-isolated converters have been taught in the previous week, including buck converter, boost converter, and buck boost converters. So you may think that so with these three converters, we are able to do three basic operations, which is step up the voltage, step down the voltage, and with buck boost converter, we can step up and down the voltage both. So one may ask that why do we need any other converter? Even the buck boost converter itself is sufficient to do whatever we want. But as you will see that all these converters have different features. So the stress on the switches, the current through the switches, the number of devices, number of components, all these are different in different converters. And depending on the application, the power level, uh, what is required in the application. So some application will require a very stiff voltage. You cannot have any changes in the voltage. Someone will require a very smooth current. Someone will require a very small size. Someone will require uh, less cost. Someone will require high efficiency. So for all these different requirements, that is why we will have different converters. So for example, here we have a Chuk converter. So it is named after the person who introduced it. And yes, this can be, you can imagine it as a combination of buck and boost converter. If you see the first portion, it is from the boost converter. The boost converter has an inductor at the start and then one switch and then another diode and the load. So from the start, it has the boost portion. And at the load side, this is the buck portion, the LC filter and the diode which will be here. So this is the buck portion. And by having these two portions, that is how we get the buck boost functionality in this converter. And so the advantage of this converter compared to, let's say, the normal conventional buck boost converter, because as you saw in the lectures that this offers buck boost functionality. The advantage here is that because of these inductors at the input side, input current side and output current side, the input current and output current are smoother. They are more continuous compared to the buck boost converter, because these are the features of buck and boost converter separately. In a buck converter, the output current is very smooth because of this inductor at the output. You don't need a large capacitor because of that. Similarly, in a boost converter, because we have an inductor at the source side, the input current is very smooth. The inductor does not allow high fluctuations or pulses in the current. So for the Chuk converter, because it has inductors on both the input side as well as the output side, the currents, input and output currents are smoother and more continuous. So that has some, for example, in the case of, let's say, PV source, if the power that is drawn from the PV is highly dependent on the voltage and current of the PV. If your current is varying, then your power will also vary. So by having this kind of a scheme where you have an inductor in series with the source, your current will be smoother. So it is required in some cases, and it has some advantages compared to the buck boost converter. The buck boost converter has switched input current as well as the output current. But the disadvantage, so advantage and disadvantage, I am comparing it with the normal buck boost converter. And the disadvantage compared to the normal buck boost converter is you can see that it has more number of components. It has two inductors and two capacitors, while the normal buck boost converter has only one inductor and one capacitor. So the filter size here and the number of components and the filter size. So this converter for the same power level, it can be larger than the conventional buck boost converter. So the point here is that you can have different converters with different features. And for some cases, for example, if you don't care about how much size your converter takes, but you are more concerned about the current should be smooth, then the Chuk converter can be preferred over the conventional non-inverting buck boost converter, or sorry, the inverting buck boost converter, conventional buck boost converter. So this was about non-isolated converters. The other non-isolated converters we have studied, and in the problem solving, we will see some more examples of the questions that can be asked. So now we can come to choppers. So choppers are basically non-isolated converters for high power rating where we use thyristors as the main switch, thyristors or GTOs. So there are different types of choppers. So, and this classification is based on the in which quadrants can the load operate. So for example, if we have the output voltage as the y-axis and output current as the x-axis, we can have four quadrant operation, four possible quadrants. So the class A chopper is simply a buck converter, and the load can be an RLE load, because usually this is used for series motor or DC series motor. So the load can be RLE load, and that is where we have the inductor. And based on that, this one can be thought of as a buck converter. And it is called a class A chopper. It is operates in quadrant 1. So positive output voltage and positive output current. The class B chopper, if you see the output voltage, since it has an inductor, it's an RL load or a RLE load, it has an inductor. And if you imagine an inductor here, you can see that from the load to the source side, to the input side, it is a boost converter. So you can see that, and that means the power will be transferred from output to input. So in this case, it is a quadrant 2 chopper, because the voltage will still be positive here, but the current will be in the opposite direction. The load will feed to the source. So you can imagine, in case of uh, some kind of a motor where we are stopping or braking, so then it will uh, send power back to the source. So it is a quadrant 2 chopper where we have positive voltage, output voltage, and negative output current. So in this direction, the current will be opposite to the direction that is shown. So this is a class B chopper. A class C chopper will be a can be thought of as a combination of both class A and class B, because class A, so uh, for the in the top left, the thyristor, and bottom right diode. So these are the components of the class A chopper, the buck chopper, and the bottom left thyristor and top right diode. So these two are the components of the class B chopper. And by combining these two, we can have a class C chopper. And because we are combining, so we will get quadrant 1 operation as well as quadrant 2 operation. So the output voltage is always positive, but the output current can be positive or negative. And when the output current is positive, you can see that the top left thyristor will conduct, and bottom right diode will conduct in the positive current direction. For the negative current direction, the uh, the bottom left thyristor and the top right diode will conduct. So I hope that is clear. So if anybody has any questions, you can ask in the chat, or you can either raise your hand, then unmute yourself. So for class D chopper, so this is now here the voltage can be negative. The current is always positive, but the voltage can be negative. So you can see the current will always be in this direction, because if the two thyristors are on, then we will get plus V in at the output. And if we turn off both of these thyristors, then the current will flow through the diodes, because we are saying that this is an RLE load. The current has to continue because of the inductor. So the current will continue to flow. But now if we are turning off the thyristor, or the GTO, then the current will have to flow through the diodes. And when the current flows through both of these diodes, you can see that the at the output you will get minus Vm. So the output voltage, so depending on the duty ratio or the firing angle, we can have a overall negative average output voltage. So that is why it can have positive as well as negative output voltage, but the current will always be in the positive direction, because the thyristors and diodes are placed in such a way that the current cannot flow in the negative direction, because the thyristors and diodes, they cannot allow current in the opposite direction to their arrangement. So that is class D. So both of these are two quadrant choppers. So the first two were single quadrant choppers, but different quadrant of operation. So quadrant 1 and then quadrant 2. So class C and D are two quadrant choppers. So quadrant 1 and 2 for class C, and quadrant 1 and 4 for class D. So now we have finally class E chopper. It's a 4 quadrant chopper. So we don't have any 3 quadrant chopper. And you can understand why. If we can have both positive and negative voltage and both positive and negative current, then we will have 4 quadrant. There is no option for only 3 quadrants. So the class E chopper has all the functionalities. The positive current can be through the thyristors, uh, and the negative current can be through the diodes. So, and the voltage is similar to class D. All the voltages, the positive as well as negative voltages, are possible. And you can see that we get more functionality at the cost of more components. So the first two choppers had only one thyristor, one diode. The next two choppers had two thyristors, two diodes. And the last chopper has four thyristors and four diodes, or we can have four IGBTs plus four diodes, or four MOSFETs, because MOSFET has the bidirectional current capability. So, but we will need more components as we require more functionality from the chopper. So this was basically about the different types of choppers. The next thing that was taught was the isolated converters, and we'll see some example in the problem solver. So we'll just come to the problems now. So the first problem is DC-DC converter can be used as switching mode regulators, and you have now four options to convert non-regulated DC output voltage to regulated DC output, or to convert regulated output to non-regulated output. Third one is to convert high frequency AC to constant DC, and the fourth is all of the above. So what do you think is the answer? Can you can put your guesses in the chat. Yes, so it is quite simple that the reason why we use DC-DC converters is that we have a DC voltage and we want another DC voltage. But the first DC voltage is either not to the level of our requirement. So for example, we have 50 volts at, but we want 10 volts. So that is one option. Another option is, let's say we have 10 volts, but it is not fixed 10 volts, it is varying, and we want to have regulated 10 volts at the output. Regulated means, so it is exactly 10. If it goes beyond 10, our converter will adjust it to 10. So it will regulate it. So the DC-DC converter is basically used to have convert a non-regulated DC to a regulated DC. So, and we will not obviously convert a regulated DC to a non-regulated. That will be that is not the function of the DC-DC converter. And high frequency AC to DC is basically that will be a AC to DC converter. So, but it is possible inside a DC-DC converter, it is possible that we will first convert the input DC to a high frequency AC, then high frequency AC to DC. So, but inside that happens inside the DC-DC converter. Overall, we can say DC-DC converter will only convert one DC voltage to another. So the answer to this one is simply A, non-regulated DC to a regulated DC. So the second question is, we have a step-down chopper, and the input voltage is 220 volt DC, and we have an RL load. The R and L values are given. We are also given the chopper frequency. So the chopper frequency means the switching frequency of the thyristor. Okay, it is because the input is DC, so there is no supply frequency, and the output will also be DC. So the chopper frequency is uh, frequency of the frequency of how fast the thyristor is switching, and the duty cycle is zero point 0.5. So what will be the maximum value of the ripple current? So this is the chopper circuit. So as you can see, we have the input voltage, which in this case is a 220 volts. And when we will turn on the thyristor, we will get that 220 volt at the output. And when we turn off the thyristor or GTO, or so it has to be a GTO because we have to turn it off, or due to some other circuitry, we will turn it off the thyristor because uh, commutation in thyristors is a different subject that is not part of this course. So when the thyristor is off, then we will get no voltage at the output. So the inductor will freewheel through the diode. And depending on the duty cycle of the device, the chopper device, we will get an output voltage. So for we are given a zero point 0.5 duty, so a zero point 0.5 duty will give us half the input voltage at the output. Now the output current, so the IA current is the output current. It will look something like this that I have shown. Because of an RL load, when we have an input voltage, it will rise, and depending on the RL value, that will determine the shape of how, whether it is more of a straight line or whether it has a curve. And then when the switch is off, the chopper switches off, during freewheeling, the current will come down. And we are assuming that the inductance is high enough because it's in millihenries. We're assuming that the current will be continuous. So the question is asking about the maximum value of the ripple current. So this delta IA is the ripple current, and so peak to peak will be the maximum value of the ripple current. So if you, in the course, it was shown that the value of delta IA, which is I max minus I minimum, is given by this equation. So in this equation, we have the supply voltage, the load resistance, and we have some exponential terms, and we require the duty, the time, the period, switching period, and tau. Tau is basically the load inductance divided by the load resistance, the L by R ratio. And Ts we can find out from by the, which is the reciprocal of the switching frequency. So we are given the values of L and R, we can find out tau. We are given the switching frequency, so we can find out the time Ts. So if you input these values and 220 volts, 10 ohms, you will get the peak to peak ripple is 2.916 amperes. So based on that, the answer to the second problem is B, 2.92 amperes. So I hope that is clear. I'll move on to the next question. So here we again have a step down chopper, but here we have only a resistive load. So for a step down chopper with a resistive load, the output voltage will be like a square wave, because we don't have any inductor which can, I mean, even in the case of RL load, the output voltage is a square wave, but the output current here will also be a square wave, because we don't have any inductor which can make the current continuous. The input voltage is given and the voltage drop of the switch is given, and the frequency is 1 kilohertz. The duty cycle is 50%. We are asked to determine the RMS value of the fundamental component of the output harmonic voltage. So the question is a bit complicated to what it is asking. So let's see the circuit. So the circuit is the same circuit as previous, but instead of RL load, we have only an R resistance load. So we don't have any inductance. And the output voltage, you can see, will look like something like a square wave. So when the switch is on, we will get the input voltage minus the drop across the chopper switch, which is VCH, minus that voltage. That voltage will get at the output. So Vs minus VCH. And we will get that up to DTS time interval. After DTS, the chopper switch is turned off. So we will get zero voltage at the output. So this looks like a square wave. And in the question, it is given that the duty is 50%. So it is like an exact square wave which goes from Vs minus VCH to 0. And it will have a fundamental, so you can understand that the square wave has many harmonic components. So it has now the fundamental component will look like something like this, and it will basically it will have an average of V, Vs minus Vch divided by 2, right? Because the duty is 50%. So that is why the average will be half of the peak. So this will be the average. And the RMS, the fundamental will start from this voltage, and then it will go to a peak value and then go to a minimum value. And now if you apply Fourier analysis to this, you will get that the fundamental will look something like this, because it will be 4 by pi and the maximum of the square wave. If the square wave was positive and negative, that means if I remove the DC component from the square wave, that means we will have zero term here. The peak of the square wave will go to Vs minus Vch divided by 2. So that is how this term comes. And then we will have sine omega t, and omega in this case will be 2 pi into the switching frequency. But we don't require the omega t here because the question is asking about the RMS value of this fundamental. So this is the fundamental of the output, and the question is asking about the RMS. And you can see for a sine wave, the RMS will be the peak divided by root 2. So the RMS, which I have shown in capital, is just the peak of the sine wave divided by root 2. And we are given all the voltages. This is 220 volts input and 2 volts is the drop. So if you put those values, you will get that the RMS value is 98.134. Okay, so the answer to this question is B, 98.13. And so if anybody has any doubts or questions, or if anybody wants me to repeat, you can just type in the chat. So the fourth question is now asking about a buck regulator. So this is not a chopper circuit, it will be a full buck circuit which will have the filter, inductor and the capacitor as well. It has an input voltage of 12 volts. The required average output voltage is 5 volts and the load resistance is 500 ohm. And the peak to peak output ripple is 20 millivolts. So the average output is 5 volts, but it has a ripple, and peak to peak is 20 millivolts. So the output is actually going from 5 volts plus 10 millivolts to 5 volts minus 10 millivolts. And the switching frequency is given at 25 kilohertz. So the question is asking that if the peak to peak ripple current of the inductor is limited to 0.8 amperes, determine the filter inductance. And the options you can see are in millihenries or microhenries. So you can see that millihenry option is 1,000 times more than the microhenry option. So if you do the question well, you can eliminate some options from there itself. So this is the circuit. So we have two switches. The first one will be a control switch. The second one can be a diode. And then we have the inductor and filter capacitor and the output voltage. So we are asked to find the value of the filter inductor. So this is how the inductor current will look like. So when the switch is on during the 0 to DTS interval, and where D is the duty, the inductor current will rise, because when this switch is on, the voltage across the inductor will be input voltage minus output voltage. And since it is a buck converter, we know the output voltage is less than the input voltage. So V in minus V out or Vs minus Va will be a positive voltage. So when a positive voltage comes across the inductor current will rise. And here I've shown the slope of the inductor current. The slope will be basically the voltage across the inductor divided by the inductance. So this slope comes from the inductor basic equation L di dt. And when the switch is off, the diode will turn on. So the second switch will turn on and the voltage across the inductor will be the negative of the output voltage. And since for a buck converter the output voltage is positive, the negative of the output voltage will obviously be negative. So we are putting a negative voltage across the inductor. So from the basic inductor equation, the inductor current will fall. And the slope will be minus VA divided by L. So now we are given a value of the peak-to-peak inductor current ripple, which is delta IL. We are asked to find the inductance value. And we know the input voltage Vs, we know the output voltage Va, and we also know the duty. We are not given the duty, but from the input voltage and output voltage, we can find out the duty. And Ts we can find out from the switching frequency. So if you, from the inductor equation or just from the graph, if you apply equation of this line, you can find out that the inductor current ripple, which is P from the top peak value to the lowest value, will be given by this equation. And now I can find, based on this equation, I can find out L, and the D term will be output voltage by input voltage, and the Ts term will be the inverse of the switching frequency. And if I put all the values, 12 volts and 5 volts, the peak-to-peak ripple is 0.8 amperes, and the duty will be 5 by 12, and 25 kilohertz is the switching frequency. I will get the inductor value is 145 microhenry. So you can understand that if the inductance was 145 millihenry, then my ripple will be 1,000 times less, because I'm increasing the inductor 1,000 times. So my so instead of 0.8 amperes, my inductor current ripple would have been 0.8 milliamperes. So, but the answer to this question is C, 145.83 microhenry. So the fifth question is again about a buck regulator, same circuit. And in fact, so all the details are same up to this point. The input voltage, output voltage are same, load current is same, peak-to-peak ripple is same, switching frequency is same, and the ripple current is again, it is said that peak-to-peak ripple is limited to 0.8 amperes. Now we are asked to determine the critical value of the filter inductance and critical value of filter capacitance. So, okay, let's see the circuit you know, and for CCM, so that is continuous conduction mode, so the inductor current is continuous. For the inductor current ripple and capacitor voltage, these are the equations that we'll get. So the inductor current equation I have shown in the previous problem, there you can come to this equation. If you just, so in here, if you just substitute VA as dVs, you will come to the other equation, this equation. And the capacitor voltage you can also find out. So in the textbooks or by the charge balance, you can find out the capacitor equation as well. And now the question has given one situation, and if you just substitute those values, you will find out that for the given condition where delta IL is 0.8 amperes and delta VC is 20 millivolts, you will find out that the L and C values are, so L value is same as the previous question, 145 micro, and C value will be 200 microfarad. So this is for the given situation, but the question is asking about the critical values of the inductor and the capacitor. So what does the critical value mean? So the critical condition or the boundary condition means that the inductor current basically starts from zero, it goes to a peak value and then comes back to zero. So, so for the normal CCM case, the inductor current will start from some positive value and then again come back to that same positive value. But here it is starting from zero and then coming back to zero. It is called the critical or boundary condition because if the ripple is greater than this, then basically we will come to a DCM condition, a discontinuous conduction mode condition, because the inductor current in that case will come to zero. It will basically come to zero before TS, and then it will stay at zero. So this situation is called a boundary or critical condition. And so you can see that in the buck case, the average value of the inductor current is the output current. So here you can see that the inductor current has a ripple, and that ripple portion of the current goes to the capacitor. So the average current goes to the load. So the average current of the buck inductor is equal to the output load current. So here the average current which I've shown, this dashed line, is equal to the load current. And so this is basically a triangle, and the average value will be just at the middle of this triangle. So that means for critical condition mode, delta IL will be twice this average current. So that is why I've written that delta IL is twice average current, average output current, and then you can substitute average output current as output voltage by output inductance and output resistance, and the output voltage can be put as duty times the input voltage. So now this equation, if you substitute in the equation of the inductor, you will get the critical value of the inductance. And you can see that the critical value of the inductance is basically given by this equation. It only depends on the duty, the load resistance, and the switching frequency. It is not dependent on the input voltage. And if you put the given values here, you will get that the output, the critical value of the inductance is 5.8 milli. And you can see that it is much higher than the basic value. And since for this value we are getting a ripple of 0.8 amperes, for the higher value we will get less than 0.8 amperes. So it satisfies the condition of the question. The question says that peak to peak inductor current ripple has to be limited to zero point 0.8. So it can be less than 0.8 amperes, but cannot be more than 0.8 amperes. And for critical value of the inductor, it will be basically twice the output current. And if you see that the output current is basically 5 volts divided by 500 ohms, which will be very small value. So for the critical value of inductance, the current will be the peak-to-peak ripple will be very small. So now the question is also asking about the critical value of the capacitance. So again, you can do the same thing that I've not shown the figure, but the peak-to-peak voltage of the capacitance should be twice the output voltage. And then if you substitute it, you will get this formula or expression for the critical capacitance, and then you substitute the values. But in this case, we will substitute the value of the initial inductor. So you will get a capacitance of 0.4 microfarad. So this is what is asked in the question, but this is not very practical. If you see, the output voltage cannot have this much of a ripple which will go from zero to the full voltage, because ideally we would want the output voltage to have a very small ripple. So usually we will have very small ripples. So for example, in the question it was given as 20 millivolt out of 5 volts. But for the critical condition, the ripple will be basically double the output voltage. So what I'm trying to say is that even though it is asked in the question, but it is not very practical. But to have a critical condition of the output voltage, the inductor current can be critical, can be like this because the output current is not really affected. The output current can still be a DC value. So anyway, the answer to this question is D, 5.8 millihenry and zero point 0.4 microfarad. So now the sixth question is asking about a boost regulator. The input voltage is given and the output voltage is also given. The load current is also given as 0.5 amperes. And you can see that the boosting is 1:3. So the output voltage is 3 times the input voltage. So just based on that, you can find out what the duty will be. So we are also given the inductor uh, inductor value and the capacitor output capacitor value, and we are asked to determine the ripple voltage of the filter capacitor. So this is the circuit, and so let's actually do one charge balance equation. So so the inductor current ripple is found using the inductor voltages. If we know what the voltage across an inductor is in each interval, we can find the ripple across the inductor ripple, the current ripple of the inductor. For the capacitor, we have to know the current through the capacitor. So you can see in the during the DTS terminal interval, 0 to DTS interval, the this switch is on, the switch which is connected to the between the inductor and the ground terminal or the zero terminal. So when this switch will be on, the other switch will be off. So the current through the capacitor will be the negative of the load current, because we are saying that because if the capacitor has some voltage, the load will draw some current, and that current will come from the capacitor. So during this interval, the capacitor has a current which is minus IA. So from 0 to this portion is IA, and the capacitor current is minus IA. In the next interval from DTS to TS, mm, the the control switch will be off, so the diode or the other switch will be on. So now we will get the inductor current will come through here. So the capacitor current we can find out it will be the inductor current minus the load current. So the inductor current has this ripple, and but we are assuming that the ripple is small, or if it is a linear ripple, then again our assumption will be valid. So the current through the capacitor will be IL minus IA. And since in the boost converter, IL is always greater than the output current, so that is why this current will be positive. And in fact, you can now we will apply charge balance because we want to know the okay, we will not use the charge balance, but if we want to know the peak to peak ripple, we have to use the current through the capacitor. So we can find out from the first terminal using the capacitor equation, which is C dV dt is equal to the current through the capacitor. You can find out from the first interval from 0 to DTS interval that the capacitor voltage ripple, peak to peak voltage ripple, will be given by IA, which is the output current, times DTS divided by the capacitance value. So the duty we can find out, we are given the input voltage and output voltage. So we can find out the duty, and TS is basically 1 by Fs. So if you substitute all the values, you will get that the filter capacitor peak to peak ripple is 60 millivolt. So again, from a 15 volts output, 60 millivolt is very small. So the output voltage can be thought of as almost constant. And that is how you will find in practical situations we will have very small ripple in the output voltages. So the answer to this question is 60.61 millivolt. So I hope everybody is understanding the solutions. So if anybody has any doubts, you can ask in the chat or you can raise your hand. So so for the next question, we can. So I will let you try this question. We can have a short break now. We'll continue from 7 p.m. So in the meanwhile, those who want, they can try this question that is on the screen. So you can try to find out the answer to this question. It's a buck boost converter, and the duty cycle is given, the switching frequency is given, the inductor value is given, and so you have to find the peak to peak ripple current. So all the information is given. You can try, and we will continue at 7 p.m. Okay, so let us continue. Uh, One person has, I think, solved the question. So the converter circuit is shown here, and we are asked to find the peak-to-peak ripple current of the inductor. So in this case, when the left switch is on, the voltage across the inductor will be the input voltage. So since the input voltage is positive, the uh, the inductor current will rise, and the slope will be the input voltage divided by the inductor value. And in the next interval, when the right switch is on and the left one is off, we will get output voltage across the inductor. And since we know for the buck boost converter, the output voltage is negative, so so based on this polarity, it is negative. So the inductor current will fall, and the slope will be output voltage divided by the inductor value. So from this, you can find out that the peak-to-peak inductor current ripple will be uh, the slope times the interval. Okay, so this you can also find from the uh, inductor equation. The LDI/dt is the voltage across the inductor, and we are uh, given all the values. We are given the duty as 0.25. The inductor value is given. The switching frequency is given. So TS we can find out as 1 by 25K. So by substituting all these values, we get that the answer is 0.8 amperes. So the answer to this one is A, 0.8 amperes. So the next problem is about a Chuk converter. So the duties input voltage is given, duty cycle is given, switching frequency is given, both the inductor values and both the capacitor values are given, and the average load current is also given. We are asked to determine the average output voltage. So this has a very whole lot of information, but the question is quite simple. So I'll let one of you guys, if you can try, because it is quite simple. So if you can try and uh, write your answer in the chat. So you can focus on what the question is asking, and then try to see what is required, what information is required. So you are just asked to find the output voltage. So can anybody provide the answer? Okay, so basically for the Chuk converter, we know the output voltage is given by uh, the negative of d by 1 minus d times the input voltage. So based on this polarity that I have shown, where the negative is connected to the input ground and the positive is the other terminal. So based on this polarity, the output voltage is given by this equation. And we only need the duty and the input voltage. So the duty is given is 0.25 and the input voltage is 12 volts. So we can find that the output voltage is minus 4 volts. So the answer to this question is minus 4 volts. So the ninth question is asking about uh, the steady state operation of a flyback converter. And we are given the input voltage, the magnetizing inductance, the turns ratio of the transformer, the filter capacitance, and the load resistance. The switching time period is 20 microseconds and the duty is 0.4. Determine the average magnetizing current of the converter. So this is the ideal flyback circuit. So it is basically derived from the buck boost converter circuit. So if instead of the inductor, if we have a transformer, or in this case, it is more of a coupled inductor, and base, so we can just change the polarity of the secondary side, and we will get a positive voltage at the output. So this is the ideal case in which we have a transformer, and uh, when we turn on one switch, that is the 0 to D interval, and then we will turn on the other switch, or it will be turned on by the circuit itself. So that is the 1 minus D interval. So the transformer equivalent we can be modeled as having a parallel magnetizing inductance, because this inductance will basically determine the rise of the current and the fall of the current. So this is how we model and analyze the transformer circuits, or so in this case, the flyback circuit. So now the question is asking about the average value of this magnetizing current, which is going through LM. So let us see that so this will also have two intervals. So from 0 to DTS interval, since the main switch will be on, we will get voltage, input voltage across the magnetizing inductance. So the magnetizing current will rise. So I'm assuming it's a CCM condition. So it will rise from some value and it will reach a peak value. And during this interval, so because we are asked to find the average of the magnetizing current, so whenever we are asked to find the average of inductor or magnetizing current, we can find that out from the charge balance. The average output voltage we can find out from the volt-second balance of the inductor, and the average current, inductor current or magnetizing current, we can find out from the charge balance of the capacitor. So for the charge balance, we need to know what is the current through the capacitor. So here in this case, we can see that the when the during the first terminal, the second switch or the diode is off, so the current through the capacitor will be the negative of the load current. So I hope that is clear. It will be a negative of the load current, and we are assuming that the load voltage is nearly constant, so the load current will also be nearly constant. In the next terminal, the main switch will be off and the diode will be on, because the magnetizing current has to continue to flow. So it will flow like this, and the diode will get forward biased now. So when the diode is forward biased, so based on the turns ratio, if Im flows through the magnetizing inductor, the current that will be flow through the diode will be Im divided by N, where 1:N is the turns ratio. And because at the secondary we are getting the output voltage across the secondary, so it will be reflected in the primary uh, as the second output voltage divided by N. And based on the dot polarity, you can see that the uh, the polarity of the voltage will be such that the magnetizing current will continue to fall. And in this case, the current through the output capacitor will be Im divided by N minus the output current. And we are assuming that the magnetizing ripple is small, or it is linear, so that we can just write it as the average value of the magnetizing current divided by N minus the output current. So here now we have, based on both of these intervals, we have the uh, how the capacitor current looks like in both of these intervals. And now we can basically apply the charge balance. So the charge balance means that the charge that is coming into the capacitor in one interval will be the same as the charge that is leaving the capacitor in the other interval. So that at the start and end of the interval, the capacitor voltage remains the same because that is the steady state condition. And the question is asking about the steady state conditions. And unless otherwise stated, we will always be considering the steady state condition. And basically, charge balance means that uh, at after every Ts time, the voltage is same. So that means the charge that is coming in is the same as the charge that is coming out. And from the current uh, waveform, we can find the charge is basically the integral of this current or the area that is bound by one region. So for the charge balance, we can say that in 0 to dTs interval times the Ia current plus uh, plus Im by n minus Ia into the 1 minus d interval. So uh, I think this here should be minus Ia. So this should be d times minus Ia. And then this whole thing will be equal to 0 because we are saying that at steady state over one time interval or switching time period, there is no charge, no net charge that is coming into the capacitor or leaving the capacitor. Because if there was some charge that is coming into the or leaving the capacitor, then the capacitor voltage after every time interval, it will change. It will either rise or fall. But at steady state, after every Ts interval, the capacitor voltage remains the same. So the net charge through the capacitor should be 0. And based on this equation, you can find out that the Im current is equal to N times the output current divided by 1 minus D. So this is the value of the average magnetizing current, which the question is asking. So, so it basically requires us to find, so we need to know Ia, we need to know D, the N is given, and Ia we can find out by first finding out the output voltage. For the flyback converter from the volt-second balance, we can find out the output voltage is given by this equation. And if we substitute all the values, we'll get 8 volts at the output. Because we are given the duty, we are given the uh, turns ratio, and we are given the input voltage, we'll get 8 volts at the output. And from that, using the load resistance, we know we can find out the output load current. And then we can substitute the load current in the average magnetizing current equation. So that will give us the average magnetizing current. Sivaram, you have raised your hand. You have a question? Sivaram Panda, do you have a question? Yes, go ahead. You can ask your question now. So you can either ask it or you can just type your question in the chat if it will take some time. Okay. So basically, this is how you use charge balance to find an equation of expression of the inductor current. In this case, the magnetizing inductor current. And so the magnetizing inductor, you can put it at from the input side as well as the output side, but here we are putting it on the input side and the primary side or the input side. And so the answer to this question is 2.667 amperes or 2.67 amperes. So D is the answer. So this was about flyback. So the 10th or last question is that a chopper may be thought of as, and the options are inverter, the DC input, DC equivalent of an AC transformer, diode rectifier, and last option is DC equivalent of an induction generator. So you can uh, put your guesses in the chat. So I think this was mentioned a few times in the lectures that power electronics in general and DC-DC converters in particular are useful because we don't have DC transformers. Because transformers only work for AC or variable voltages and currents. Because the flux has to change some other uh, for some other voltage to be induced in a coil. And for DC, because there is no change, so there will be no induction in the coil. So that is why we don't have a DC transformer. And that is why a chopper, which is a DC-DC converter, it can be thought of a DC equivalent of an AC transformer. That means that we are able to perform the function of the transformer, which is stepping up or stepping down the voltage. And but we are doing it without, I mean, that is the function of the transformer, and that is what the chopper also does, but for a DC case. So the answer to this question is a chopper is just a DC equivalent of an AC transformer. So that was all the questions that we had today. So I could not go into details about the isolated converters. Uh, but I can just briefly talk about why do we require isolation. So there are a number of reasons why we require isolation. So flyback is like one of the basic isolated converters, but uh, we require isolation for a few reasons. One can be for safety purposes, or yeah, Sivaram, you can uh, either ask your question quickly or you can type it in the chat. So you can unmute and ask as quickly as possible, or you can just type in the chat and I will read it. So one of the reasons why we require isolation is for safety purposes, because in many cases the output or the input has some sensitive components, so that any problem that happens in the input or output should not be transmitted to the other side of the converter. So by having isolation in the converter, so there is no direct connection. So that basically provides us that safety option. So it can also, uh, for if we want to reduce noise in the circuit, because when we are switching, by switching or some high frequency noise, if there is in the circuit, in one side of a circuit, so the grounds get corrupted. Why magnetic reset is not there in, I cannot read what you have written at the end. So if you can write it in English. So I was saying that the noise, because of this isolation, the noise is not propagated. So that is another reason why I may use isolated transformers. Another can be uh, if we want to have an output which is not at the same ground as the input. For example, if we want to connect another circuit in series at the output, so sometimes that is not possible in non-isolated converters. But with isolation, we get the output, because the output terminal is isolated from the input terminal. It can be connected to other converters in series or in parallel. So So these are the main reasons why we use isolated converters. So Venkatesh, if you can ask your question in English because I cannot. Okay, fly back. So actually, magnetic reset, what it basically means is that the current should. Uh, so in isolated converters, because we in transformers or even in ferrite inductors, we don't want the current to go beyond the saturation point because as the inductor or the transformer gets saturated, it will basically lose its functionality as the inductor or transformer. And in some cases, it may act as a short circuit also. So we want to avoid this condition. So so basically, we don't want the inductor current to go beyond certain point, and similarly for the transformer, we don't want it to go the transformer current to go beyond a certain point, the saturation current. So that is why uh, what is what is called a reset. What we mean by resetting is basically we want the transformer or inductor current to come back to the original value, and it should come back to the actual original value. If there is some shift, if it is slightly higher than the original value, and that value will keep on accumulating in further cycles. So the average current will keep on rising, and the peak current will also keep on rising. So the inductor or the transformer may get saturated. So that is why we have to make sure that the current basically comes back to the original value, and that is so that it does the transformer or the inductor does not get saturated. The reset circuit, so it depends on the converter how it functions. So the flyback converter is basically it functions by so it is different from other transformer based converters or isolated converters in that the uh, the transformer basically stores energy. That is why it is not strictly a transformer because the transformer by definition it will not store energy. It will directly transfer energy. But as you can see, the flyback converter is designed in such a way that in DTS interval, the output side is disconnected. So there is no current in the secondary. So current is flowing through the primary, but there is no current in the secondary. So so the transformer is basically storing energy. That is why it is not strictly a transformer. It is more like a coupled inductor. The two windings are coupled, and the energy is stored in the flux of the transformer, and in the second interval, that energy is transferred to the secondary side through the secondary side to the load. So that is how it works, and uh, I mean, the energy is reset, the flux is reset. So flux goes from some value. The flux will have the same shape as the magnetizing current. And so here I have shown a CCM condition. We can operate it at boundary as well if we want to uh, utilize the, the transformer in a better way. So I hope that is clear. So if anybody else has any questions, Sivaram, if you have a question, you can either type it or you can unmute and you can ask your question. Yes, these all these PPTs are shared. So if you go to the course portal, so you have on the left side all the week one, week two, week three, and at the bottom there will be some link for recording, session recording or something like that. And there you will find uh, you will find a Excel sheet, and in that Excel sheet, all the three problem solving sessions that we have on Mondays and Tuesdays, the the lecture link, YouTube link, uh, and the slides, the link to the slides will be given. So I have also provided the link to the slides in the YouTube link, the description of the YouTube video. So there you can find these. Okay, so if anybody does not have any more questions, then we can. Why does working? What does working flyback converter in industrial area? Uh, so in industry, if you want to know in practical where we use this, so flyback is basically used for low power applications in uh, very small converters where we require isolation. So mostly like your chargers will have some kind of flyback converter. So they will first have F. So for example, if uh, uh, your laptop charger or your mobile phone charger, it works on your single phase AC, which is 230 volts RMS. And but you want what at the output it will basically be very small voltage, and it will be a DC voltage. So first we will have a boost PFC. So that boost PWM rectifier that is taught in the previous week, I think. So that one will have a full bridge rectifier first. So we will get a rectifier voltage, and then we will have a boost converter. So that will give us a regulated output voltage, and the power factor will be uh, close to unity. And then we will have a flyback circuit. So the flyback, based on the transformer turns, it will first reduce the voltage, and it will be controlled in such a way that we will get the required regulated output voltage. So that is one application of the flyback converter. So in general, it is used for these low power applications where we require isolation. And so another application of these isolated converters is that when we want to have a very high step up or step down ratio, because let's say if we have 230 volts or 300 volts peak and we want a very small 5 or 10 volts at the output, if we have a normal buck converter, our duty ratio will be very small. And that will lead us to, so very small, to generate very small duty ratios is also a problem. It is not very simple. So if we instead have an isolated converter, the turns ratio will give us some uh, step down itself, and then we can have a medium duty ratio of 0.5, zero point 0.4, which is easier to generate and maintain. So that is another reason why we use isolated converters. Any other questions? Uh, Three-phase converter. So which three-phase converter do you mean? Do you mean DC to AC three-phase converter? Or are you talking about the rectifiers that we have studied previously? So just clarify which three-phase converter you. Okay, rectifier. Uh, so I don't have the circuit drawn here. And so I'm basically on my laptop. I don't have a pencil or to draw the circuit, but uh, basically, if you go to the YouTube lectures, you will find in the second or third week I talked about the three-phase rectifiers. So basically, the point in three-phase rectifiers is that you have to find out that the SCRs or the diodes, they will be connected in common cathode or common anode configuration. And then you have to find out if it was a, let's say, a common cathode configuration, you have to find which anode voltage is the highest. The anode voltage that is the highest, that diode or SCR will conduct, or it will be in a conducting position. And after that, you have to see based on which diode will conduct what will be the output voltage, and then you will get the output voltage. So you can uh, see those videos that from lecture 3 or 4. So those lectures are on YouTube. Okay, so if we don't have any more questions, so those who are uh, people can leave. I will be here for 10-15 minutes. So if anybody has any question, they can ask. Other people can uh, they can leave. Okay, someone is asking about just a recap of the session. Okay, so Newton is asking about DC to AC conversion. So I think in the next week we will be talking about DC to AC converters or AC to DC, and they are both quite similar. So in the next week we will just address those converters. So as for the recap, so this week the topics that were taught were non-isolated converters were continued, and then we had different types of choppers and isolated converters. So in non-isolated converters, what was taught was a Chook converter. So I mentioned that the choke converter can be seen as a combination of a buck and boost converter. So on the input side, it has the structure of the boost converter. It has an inductor and then a switch. And the output side, it has the structure of a buck converter. Has an LC filter and then a diode here. And if these two are combined, the buck and boost converter, we can have an intermediate capacitor and we will get a choke converter. So the choke converter is also a buck boost type of a converter. The output voltage is D by 1 minus D times the input voltage, where D is the duty. So it can produce both voltages less than the output input and more than the input. So it's a buck boost converter. But the question is, if we have the normal buck boost converter, Why do we require another buck boost converter? And the answer is that it has certain advantages over the conventional buck boost converter. So because of the inductors in the input side and the output side, the current input and output currents are continuous. So in a buck boost converter, if you see that the input current is actually uh, discontinuous current, it goes to the inductor current and then it goes to zero. So because of this, the structure of the Chook converter, the input and output current both are continuous in this case. But you can understand that compared to the conventional buck boost converter, this Chook converter has more components. It has two inductors and two capacitors compared to only one inductor and one capacitor in the normal buck boost converter. So we get some advantages and we get some disadvantages. So it depends on the application. If your application wants, it's very sensitive application where you want to have continuous input and output currents, you can use a chip converter. But if the converter size is a constraint, if you want to minimize the converter size, if if you want to fit it in a small package, then you can prefer the normal buck boost converter. So this was about uh, non-isolated converters. Then we came to choppers. Choppers are basically DC-DC converters for high power ratings where we use thyristor or GTO as the main switch. So so the output in this case is can be an RLE load. So like a DC motor, it can be an RLE load. And in that case, so now the classification of choppers is done in basically on the basis of the in which quadrant the output we can have the output. So based on this convention, we can have four quadrants of the output. If the output voltage is positive, output current is positive, then is out first quadrant. If output voltage is positive but current is negative, that is second quadrant. If both are negative, then that is third quadrant. And if output voltage is negative but current is positive, that's the fourth quadrant. So class A and class B choppers are called single quadrant choppers. For class A, this is just a buck converter or a buck chopper. The output voltage will be less than the input voltage, and the power will flow from the input side to the output side. So the output voltage and output current both will be positive. So it is a quadrant one. It is a class A chopper. Class B chopper is uh, it can be thought of a boost converter from output to input. Okay, but from input to output, it is still a buck converter. But from output to input, it can be thought of a boost converter. So the current will flow from the output in the other direction. So it will be negative output current but positive output voltage. So it is a second quadrant chopper and a class B chopper. So now both of these are single quadrant choppers. So now we have class C and D, which are two quadrant choppers. And you can see that class C is a combination of class A and B. So in this way, we can have both these functionalities and we can get quadrant 1 and quadrant 2. Class D, we have the current will always be positive because if you see uh, when the two SCRs are on or GTOs are on, the current will flow in the positive direction, and when they turn them off, the current will again flow in the positive direction through the diodes. So there is no option of negative current flow because the negative current cannot flow through the diode or it cannot flow through the SCR because both of these are unidirectional devices. So that means they can only allow current in one direction and they are arranged in such a manner that the load current cannot be negative. But the load voltage can be negative. When the two diodes are conducting, then at the output voltage is equal to the minus input voltage. And depending on for how long the thyristors and diodes are conducting, we can have an average output voltage that is negative. So we can have both positive and negative output voltage, but the output current will always be positive. So we can have one and four quadrant operation. So this is about two quadrant choppers. Finally, we have four quadrant choppers, which is class E chopper. And in this case, if you see that the negative current flow can be through the diodes as well, because we now have more diodes and more thyristors here. So we can have both uh, the current as can be positive and negative, and the voltage also can be positive and negative. So in this case, we get four quadrant operation. So for the motor, it is said that uh, because we can have the motor can be running in one direction, and if then we apply brakes in that direction, then the current will be reversed. So for the same polarity of voltage, the current can be reversed. So that is forward braking. And then we can have the motor can be running in the reverse direction. And so that is reverse motoring. And then if we apply brake in the reverse direction, then that is reverse braking. So uh, these basically form four regions: forward motoring, forward braking, reverse motoring, and reverse braking. So these apply for the four quadrants. And depending on what kind of a motor you are using, what application is for your motor, if you want all these regions, then you can have the class E choppers, and you get more functionality at the cost of more devices. So the single quadrant choppers only have two devices, one thyristor or one GTO and one diode. Two quadrant choppers have two thyristors and two diodes, and the class E four quadrant chopper has four thyristors and four diodes. So this was a summary of the choppers. Uh, and finally, we talked about isolated converters and what is the reason why we use. We basically use them for safety reasons, for to prevent noise, to get an output voltage that is not at the same ground as the input voltage, and finally for very large transformation of voltage from very high voltage to low voltage, or very low voltage to a higher voltage, we can use isolated converters. And then uh, for the problem solving, you can see the lecture. It will be uploaded on YouTube. So if anybody else has any questions, yes. So based on how we define the terminals, yes. So here I have defined the positive current will be that current which goes from the positive output terminal to the negative output terminal. So if now the current goes in the reverse direction, then that is a negative current. Okay, so for class B chopper, the current will flow in the negative direction. And you can see that the diode and HCR are in such a way that it can only allow negative current. Because if we have a positive current, the diode will not allow, the SCR will not, thyristor will not allow. So class B chopper can only allow current from uh, the negative terminal of the output voltage to the positive terminal. And that is why you can see that in class B chopper, it basically the output side behaves like a source, because for the source, like the current flows from negative to positive in the negative to positive direction, and it goes out of the positive. So that is what is happening in class B choppers as well. So that is why it is uh, energy or power flows from the output to the input. So I hope that is clear. Okay, so I am basically we are talking about uh, the convention and the directions of the voltage and polarity of the voltage and direction of the current. So in all cases, I have taken one direction of one convention for the voltage and one convention for the current. So uh, if the actual voltage that we get at the output, if it is if it is for the same polarity as the what I have shown here, then we will say it is a positive voltage. If we get more voltage at the positive terminal, then if the potential at the positive terminal is more than the potential at the negative terminal, then we will say it is a positive output voltage. If, however, the potential at the positive terminal is less than the potential at the negative terminal, then that will be a negative voltage. For example, you can see class D chopper. If the two diodes are conducting, so you can imagine the two diodes are conducting, then this will be the what I'm showing from using my mouse, my cursor, that will be the circuit. And the V output voltage will be minus V input voltage. So in that case, we will get a negative voltage at the output. And similar, but here you can see that the current can only be positive based on how the convention is defined and how the switches are placed. Because the negative current means current flows from the negative output terminal to the positive output terminal, and that is not we can that the thyristor and diode will not allow that. But in the case of a class B effective chopper, the current uh, the devices are placed in such a way that they only allow a negative current. So they only allow a current that flows from the negative output terminal to the positive output terminal. And you can see if that direction continues, it it can then flow through the diode or through the SCR. But positive current cannot flow. Positive current means that is from the positive output terminal to the negative output terminal, which I've shown in this arrow. The arrow shows the positive direction of the current. In for class B choppers, positive current is not possible. That is why it is only second quadrant. So I hope that is clear now. Okay, so if we don't have any more questions, then we can conclude for today. The slides will be made available and the lecture will be uploaded on YouTube. You can find the link to the lecture in the course page, or you can search on YouTube NPTEL sessions by Saleh Khan, Saleh. If you search that on YouTube, you will get the channel and all the videos will be there. Okay, so thank you all for joining. We'll conclude then today.